Our next speaker is the president of Northrop Grumman Space Technology, Dr. Alexis Livanos. Dr. Livanos studied engineering and physics in the United States. He spent 28 years working in the defense and space industry in the U.S., many of them with TRW, which is now known as Northrop Grumman Space Technology, where he leads the company's space technology business sector. Over his career, Dr. Livanos has been directly involved in the successful launch and operation of 43 satellites. Those of us associated with the space business know that the key word in that last sentence was success, something that often eludes us when we try to launch satellites into space and make them work successfully. Dr. Livanos is also known as an innovative leader with extensive international experience. With that in mind, I look forward to hearing from him on how we can integrate space and other systems at the global level to meet the challenges ahead. Dr. Livanos. And could we have a light over the podium, please, if that's possible? I see, unless there's... we don't need one. I just learned how to make it work.
Thank you, Jim. I would like to give you a little bit of historical background and put the problem in the right context as to why we need this system of systems and what it's going to do for us. For centuries, the weather observations consisted basically through the use of the human eye or the human senses. The first actually document that I've ever read on climate and weather prediction is called the Farmer's Almanac, which was first started in 1700. And it's a very colorful document. They still publish it, but the data is a little more modern. It does have some arcane theories in it. The basis for which the almanac was put together had to do with the rain gauge, the barometer, anemometer, thermometer, and hydrometer. And I think we've used those instruments forever, still are using them. The communications that actually started in the 19th century enabled people to communicate that data back and forth. Therefore, we could start making weather maps and we could predict actually what was going to happen, but our prediction capability was really a few hours because that's all that we could do. The advent of the satellites and more powerful computing systems on the 20th and 21st century has extended the prediction capabilities to days. Now we're talking about confidence, what's going to happen in 3 days, and when you look at weather.com or any of the services, you will see that now we can predict even sometimes longer than that. The early satellite climatology produced very, very low spatial and spectral resolution images. On the left-hand corner, you'll see an example of Tyrus, which was essentially a black and white television set. It was produced very early on, and the next generation satellite was launched in the 70s, and that was Earth Resources Technology Satellite, which was also known as Landsat, and it's known as Landsat now. And it was a phenomenal achievement at the time. We went to 2 IR bands and we had a resolution of about 80 meters. Compare that with what we have today or what you can get out of Google. And the next generation of satellites, as you can see, were the satellites, a number of satellites, for example, POESS is one and DMSP is another one that had been used for weather prediction. In the next slide, we can actually see what some of the existing assets can do. And I won't go through the details in here, but look at the difference, for example, in polar ice cap over the last 7 years. These are pictures taken. You can actually see the ozone depletion regions as they develop, the tracking of the hurricanes. We can look at cloud cover, and then we get real-time global weather. In the next slide, you can actually see how many nations and how many satellites are either on orbit, on the planning stage, or actually being fabricated. It is actually an astonishing number, and all the countries involved in terms of putting those assets in place. And as you can see below, those squiggly lines actually denote what the paths are for those satellites, which are mostly at the low Earth orbit, but there are a few geosynchronous satellites. But what those satellites do essentially is they can't quite put the whole puzzle of climate and weather predicting together. It's still there are pieces that are missing. And let me explain in the next one why that is the case. It's the weather and global prediction, or the climate is the whole problem is not local, it is global. We have learned that weather and climate don't respect national borders. A volcanic eruption, for example, you can see on the right, taken by 7 different systems, all owned by different countries, produced enough CO2 that affected actually the quality of air around the world. And on the picture on the left, which shows some of the Sahara winds blowing dust in the Atlantic, where there is some conjecture that that actually could have been the cause for some of the thunderstorms and some of the issues that we had in Florida with the weather patterns in the last year or two. So weather effects are global. And the next slide shows us the fact that a universal methodology is necessary. I think we talked a little bit about doing all of the data acquisition from the bottom, from buoys. We get a lot of information on wave motion, for example. We could in the future get information about tsunamis. We get information from balloons. They still send them up to look at the weather at about 100,000 feet. We send unmanned spacecraft now, as well as manned, through the hurricane and an eye of hurricane to map the temperature as well as the pressure profiles. And then we go up to LEO, low Earth orbit satellites, where we're looking at a number of observations. And then finally, we're going all the way to GEO, where we're taking high spectral quality images from the 24,000 miles in the air. So that's what we need in one dimension. We need to look at the entire nadir column, all the way from 23,000 to subsurface. But that's not enough. That's just one point. In order to have a complete story, we need to map that all around the United States. That by itself is a formidable thing to do in terms of the assets, in terms of the spectral, in terms of the spatial resolution, in terms of all of the sensors that are necessary. But the part that makes it even more difficult, and why it is such a difficult problem, is because the physics that basically govern those effects are extremely difficult to deal with, even with the use of modern computers. For those of you that have yet remember some of your high school or college mathematics, the nonlinear differential equations that describe them, there are at least 4. They have to do with thermodynamics, they have to do with Coriolis forces, and they're highly dependent on different conditions, on altitude, they're interdependent, and it's a very, very, very tough problem. So what I would like to then come to, which would be the next slide, is basically what I call the paradigm for the future. We have been talking about the methodology for systems that will ensure all the measurements that will be deployed, maintained and operated and fed into an Earth system, monitoring laboratories and decision support tools to assist policymakers and management decision makers. And as was mentioned earlier, this is based on the principle of the initiative, the Global Earth Observation Systems of Systems, or GEOSS. Most of the countries here tonight actually are signatories of GEOSS. And it is that system envisioned as a complex system of sensors, communication devices, storage systems, and computational devices. Now what we have to do is we have to make it real. And what I would like to spend a couple of minutes talking about and concluding my talk to meet the 10 minutes is what are the next steps. I think you just heard on the previous discussion about how Dr. Ryan described the framework of the 26 essential climate measurements that we need to take. 26, and it has taken a long time, but there is finally a guideline. There is a requirement. So what do we do with that? How do we go from here? As you can see on the chart, this is a blueprint, and that is what I'm saying is the next step. The next step is to put together a blueprint as to what the system is going to look like. And it sounds like a simple proposition, but it's not, because that blueprint has to be iterated a number of times. And I think the previous speakers talked a little bit about what those iterations are. First of all, we need to look at cost for the system. A lot of the systems that were launched were research that pushed the state of the art. The cost in terms of putting a global system together would be unaffordable. So we need to figure out exactly what the cost, how to reduce the cost for those systems. And one of the ways of doing that is looking as to how we can develop and share that capacity and the capability between the systems. It is not necessary to take 7 pictures of an eruption of a volcano. One system is enough. We'll trust somebody else to do something else, like look over at the Sahara Desert or look over at the ocean temperature. So we need to figure out how to optimize the capability and capacity of the system as a function of cost and update that blueprint until we arrive at what we think is the optimum. And that's a tough thing to do. And it's a tough thing to do because of the complexity of the problem, because of the numbers of people involved, but I think this is really the only solution. From my perspective, from Northrop Grumman, we are dedicated towards supporting that solution. We do solve the tough problems. And I think we have worked really hard the last few years in terms of investing in some of the tools that are necessary, that some of you have seen as to how that data can be actually handled. So the opportunities that are coming up in the future for us to support, I think they have a can I have a glass of water, please? They have a precedence. The precedence was set, I think, in the early 1990s. As a result of that precedence, I guess there was the UN agreement on climate that established the framework. We have been working closely, us, through the United States government, and the United States government with other European countries, such as Europe, the European Union, Japan, India, and many others, put together some systems that actually currently supply some of the data that is, as somebody said earlier, shared freely, should be shared freely with the rest of the world. A lot of the EOS systems, the Terra, Aqua, and the Aura, all those systems form some of the basis for the climatology. So what I would like to close with is I'd like to remind us all that we just share one small planet, and it's all we have. So we need to use this particular occasion in here to work closer together, to support each other, build some trust, build some relationships, because we need to go forward, and the problem that we have to solve is a very difficult one, and it will require real dedication and cooperation from all of us. Thank you.